Morning.
I went to Goodwill a couple of weeks ago, and I found these ISS mission stickers. They're so cool.
Oh, nice. I was wondering where you got those, or what they were actually. That's cool.
They were just in a poster set at Goodwill.
That's pretty cool.
Have you checked out the new farmers market yet?
Which farmer's market?
On Thursdays at Hawthorne.
No, I haven't been since like they reopened or whatever.
I've been trying to go every week because it's you get matching bucks if you have SNAP benefits.
Oh,
It's
nice.
a really nice economical way to get fresh veggies.
All right, let's get started. Any questions, comments? So of course we'll have our lab finals. So if you couldn't make it on Tuesday, make sure you come today. And then I think I have one person making it up on Friday, so if you need to make it up. So quizzes we could either do today, like during lab, like so if you don't have lab, or after, because honestly the lab final doesn't take you that long. So yeah, today would be ideal to finish quizzes. If not today, Friday or email worst case, yeah.
And the lab final is like open notes so that we can get our old labs.
Yeah, so.
Are we able to get some of our old labs? I'm wanting to see a couple of those.
Yeah, so I attempted to grade some. So if they have a grade, they've been entered and I'll hand those back and you can keep them. Otherwise, I'll hand them back during lab ungraded and then you'll have to hand them back to me.
Sounds good.
Yeah, otherwise the labs are online so you can look at them. And then papers ideally due today. I was preferring paper copy, but email is also fine. If not today, tomorrow, but I would like them by this week or weekend if you're running behind. I just don't want them dragging into next week. Other questions, comments? So yeah, I think I'll be on campus tomorrow at 11. So if you, like I said, if you have multiple labs to make up, be there at 11, and please email me what labs you need to do. And then otherwise, people have been emailing me if they're going to be a little late. So, you know, again, just email me and confirm. Oh, and then one last thing. So since someone is taking the exam early, the exam is written. And then please tell me who else is taking it early, because I'm going to take it over right now. I think, right, you said? Yeah, or like testing center. So basically alternative testing plans. I feel like somebody else talked to me.
Yeah.
And okay, perfect. Yeah. So let me know. So now you can schedule it, because I've written it as silly testing center policies. But that's where we are on that front. But yeah, I just have to get your name down. Very policy driven. Anyways, let's continue with chapter 19. And so then we want to just look at our buffer solutions. And so this kind of, again, we want to think of Le Chatelier's principle. Uh-oh, what's going on? Oh, sorry. All right, there we go. Wakem's back. All right, so again, we're thinking of kind of Le Chatelier's principle of how we can stress it and what happens. And so let's just define a buffer solution. So we had mentioned that, of course, blood was a buffer solution. We have to keep, right, our blood at a tight pH, of course. And so a buffer is just defined as any solution that resists a change in pH. And you can add either an acid or a base. And again, it should not change too much. And so then we'll see how this works. So first, we'll kind of neutralize the components of our buffer, and then Le Chatelier's principle, right, will help reestablish equilibrium. And then to make our buffer, we of course have to have a weak acid and then its conjugate base. And so we can think about, right, what that might look like. So if we're doing acetic acid, right, what's its conjugate base? Acetic acid. Yeah, acetate. So we could pick any, right, appropriate acetate salt. So, you know, sodium acetate, potassium acetate, whatever. And then, right, if we're going the other way, so we could, of course, if we're doing a weak base, base one, we need the weak base, a conjugate acid. And so our classic example would be ammonia. And then what would be a conjugate acid? Salt of ammonia.
Be ammonium, right?
Yeah, so ammonium, and then did you say counter ion?
No.
So ammonium, and let's just pick chloride. So right, ammonium chloride. I wouldn't pick fluoride. So why would fluoride be a bad choice? Yeah.
It's really electronegative. And wait, what am I saying?
Kind of, yeah. What's it the conjugate base of?
Oh, it's the conjugate base of HF.
Yeah. And so we'll get to this a little later, but I had mentioned this as our safety tips, right? So remember, if we have our conjugate base, so right now our fluoride, and then that means we can also write the reverse reaction, essentially. So you always want to be thinking about the reverse reaction, right, for your weak acids and bases. So you don't want to confound things by picking salts that are, in a sense, basic, right? So again, let's write our Kb for HF so we can remember. So all we're saying is fluoride can react with water to reform HF, and then we'd make hydroxide, right? So thus, our fluoride is a basic salt. And so not the best buffer choice, unless you were trying to make a complex buffer, but right, we're not there, or, you know, that's not here nor there right now. We're just focusing on our basic buffer, so we don't want to confound anything. So yeah, keep that in mind, and again, this is our Kb reaction then. So this just gives us our Ka reaction, right? These are all your Ka equilibrium reactions. But you can take the base, right, your conjugate base salt, react it with water, and find the Kb reaction. All right, so back to our buffers. And so again, other buffer systems. And so blood also has carbonic acid and our hydrogen carbonate ions, so of course, right, just differing by a proton. So there's our acid-base combination. And so again, we have to have significant amounts of both our acid and our base. And so there's our solution. So again, like we predicted, acetic acid and sodium acetate. And of course, you can mix them together. And so then again, right, kind of thinking Le Chatelier's principle. And also, I don't think we'll get into the math this quarter of this, but we'll kind of continue with acids and bases next quarter with the rice, and you'll be doing some more of this. So you can kind of think about where the math will be going. And so essentially, right, you have your buffer solution. So again, we're thinking about our acidic buffer. So, okay, it's this, right, our acetic acid, sodium acetate, for example. And, okay, let's just thought experiment, think through this. What happens when we add our strong base? And of course, right, we could overwhelm our buffer if we just like dumped in a lot of strong base, but that's not what we're trying to do. We're saying, okay, we're adding a small amount. And so the first thing that's going to happen is we'll have our neutralization reaction. And so that's essentially where we're going, right? So eventually you'll do the math, do the stoichiometry, cancel out, blah, 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 right? So then they'll do the neutralization reaction, which, oh, what does that form there in your neutralization? What's that same species? Yeah, it's sodium acetate, which is your base, right? So it's your conjugate base, so that's part of the trick here. So, okay, you're making your conjugate base. And, okay, well, now let's think about equilibrium, right? So then you have your solution. So, okay, how it works. So again, right, we do our reaction, and then now our equilibrium, right, will shift. So then after you do your reaction, again, you've made your conjugate base, and then if you need to reform your acid, right, it can go back and kind of remake acid, or acid can disassociate, right? So to keep your pH kind of the same. So again, same thing, right, your buffer also has a base part to neutralize. So if you have your same acetic acid buffer, right, well, now we can take our hydrochloric acid, for instance, neutralize it with our base, right, our conjugate base. And then what are we reforming? Yeah, our conjugate acid or our original acids. Of course, right now this is a conjugate acid just because it's on the product side, but was our acid. So yes, right, we can make our acid. Again, you're thinking of equilibrium, back and forth. So once you make acid, it could go back and disassociate, right, and make sure that your pH does not change too much. And again, it does mention that it has to be less than the amount of moles, right, of our sodium acetate or our base. So, right, we can't overwhelm our buffer, is what that's saying. So otherwise, right, our pH change is small. And so again, right, it's trying to show us that it does our reaction, and then, right, we can shift our equilibrium to try to keep our hydronium concentration constant. And so then there's also kind of this cheat sheet equation, which we can use sometimes. And so this is valid when we have the 5% approximation. And so then this formula works. And so usually, right, if you're given like a buffer and kind of their acid base, then you can use this expression. And then later we can use this, like I said, with the approximation. But this helps us figure out kind of like our starting mixture pH. And so, right, you can see where we'll have our ratio of our base, right? So AKA, this is going to be our acetate, for example, and then over our concentration of our acid. So, right, again, in this case, acetic acid. And so these would be in molarity, as usual. And then the other thing that you'll notice is I believe your homework has a slightly different formula. It's probably given in the form of pH equals pKa minus the log of acid over base. And so note, right, they're the exact same formula. This one just has a plus sign since it's base over acid. This one is minus since it's acid over base. I prefer this one just because I like positive signs, and I don't know, I remember base over acid for some reason. But I'm just warning you, right? Same form. And so like I said, right, we'll practice this situation so you'll see what we mean about when you can, just jump and use this formula in some of our equations. Otherwise, we'll solve it the full method with rice. So rice will continue to be with us, like I said, next quarter. All right, so let's get into this classifying salts, because it's important. All right, so let's go through this. And so it's a lot of words, at least in this first part, but let's break it down because it makes it sound kind of confusing, but it's not. All right, so let's look at our first statement. So it says, if our salt cation is a counter ion of a strong base, okay, well, let's check that out. Right, okay, well, let's just start with sodium. And so it's saying, right, counter ion of a strong base. Well, what's sodium paired with, right? Hydroxide. And I like to do this analysis. And so sodium, so right, the base it comes from is sodium hydroxide. And well, we know sodium hydroxide is a strong base, so right, it's going to fully disassociate. So if it's going to fully disassociate, right, we're saying that the sodium can't act as an acid, right? So it's not going to accept electrons. It's not going to do anything weird with water. And so that's what it's saying here. So salt cation, counter ion of a strong base. So okay, does not react with water. And then let's look at the second half. Anion is the conjugate base of a strong acid. So now you're looking right at your chloride. And easiest thing is just trying to add, right, a hydrogen to it. Oh, well, that's HCl. Okay, well, we know that's our strong acid. So that's going to fully disassociate. And so if you, right, if you have trouble with this, go back, if I can find it now, to the chart that I handed you, right, this acid chart. So you could go back, look at this. Oh, yeah, does not undergo base ionization in water, right? It's not going to reform our base, right? It's not acting as a base. That's what it's telling us here. Or again, right, our strong acids. Okay, strong acids fully disassociate. All right, so then, again, if it's our conjugate base then of our strong acid, right, it's essentially not a base because we said, again, this reaction will not occur, right? It's not going to pluck that off. That's, again, the implication of that arrow. All right, so then in that case, neither ion reacts with our water, and so we have a neutral salt. So sodium chloride is neutral. And then let's just go through that analysis. And then you can start to see, right, once you establish that a salt is acidic, basic, or neutral, then you just kind of know it. Let's see, what was our next example? I already forgot. Calcium nitrate. So again, right, just do your analysis. So what base is calcium paired with? Right, make it simple. So what base does it come from? Huh? Hydroxide? Is that what you said? Yeah, say it. Yeah, that's correct, right? It's the simplest base form, just tacking hydroxide on. But then we know it's our ionic compound. So, okay, it's going to fully disassociate. So now we're just proving, well, calcium is neutral. Let's do the same for nitrate. Sorry, I should have written calcium nitrate over here. And so then what acid does nitrate come from? Yeah, nitric acid. And then what do we know about nitric acid? So is it strong? Is it weak? Right, go back to your chart. Yeah, strong. Oh, I can't even find my chart. So strong, again, right, remind yourself, okay, they're at the top. Equilibrium lies all the way to the right. So there's my single arrow. So, okay, that means my nitrate then is also neutral. Okay, so that proves that statement. So right now we're saying that nitrate salts are neutral, calcium salts are neutral. Let's just prove that, right, with KBr to show that, yes, it's neutral. we have KBr. So what base is associated with potassium? Yeah, potassium hydroxide. So again, fully disassociates. So, okay, that means potassium is neutral. And then bromine, what acid is it associated with? Hydrogen, so hydrobromic. And then is that strong, weak? Strong, so fully disassociates. And so now we're saying, okay, again, our bromine is neutral. So overall, neutral salt there. All right, any questions so far on the neutral one? All right, so now let's break down the next statement. So, okay, the salt cation is a counter ion of a strong base. Okay, well, that's going to be neutral. But now it's telling us that the anion is the conjugate base of a weak acid. And so then it reminds us, okay, cation is neutral, but then our anion will be basic. And so let's just prove that. So let's analyze sodium fluoride. We kind of have done fluorine, but let's just do it again. So sodium fluoride, and again, you can kind of do these analysis a little faster. So sodium, of course, what base is it associated with? Hydroxide. So again, fully disassociates. So we know our sodium is neutral. But now we look at our fluoride. And what acid is it associated with? So HF. And now what do we know about HF? So weak. So now we have this equilibrium, right? So now we're saying, okay, it partially disassociates. And again, because we have this equilibrium, let's write what our fluoride can do. And so again, now we're saying because we have equilibrium, our fluoride plus water, let me write it out mechanistically. Looks a little better. So it's saying, yes, fluorine, though, is strong enough to pluck off a hydrogen. And so like we mentioned, reform HF. And then form hydroxide. So that's the other key, right? So that's why it's basic. So now definition of a basic solution, forming hydroxide. So fluoride is then basic. Sorry, you had a question?
Well, I was just going to say that our blood buffer so does not free radicals.
Probably not like free radicals, but just yeah, the chemistry of your reactions has to take place at certain pHs. And I'm not the best biologist, but yeah, my understanding is everything has to be to a certain pH. You got hydrogens going back and forth at all your transport, so you start messing up that equilibrium a lot, that'll be pretty bad. And I'm sure your blood is a complex buffer, because it has carbonate and also phosphates in there. And I'm not sure what else is in your blood. All right, so does that make sense for fluorine or fluoride? Why it's basic? Make sure, ask questions. And so let's go through that analysis for calcium acetate here. So that's part of, I guess, the trick of this chapter too, is recognizing these little ions. And of course, you can use your polyatomic charts. If you need new ones, let me know. Calcium acetate, and I can draw you acetate all day, but I can never remember the formula. All right, so now we have our calcium acetate. So again, we'll go through our analysis. So what do we remember about calcium? What base is it from? Is it acidic, basic, neutral? So neutral, right, it's from hydroxide. We want to go through the analysis real quick. Just kind of make sure we're all on the same page. So yes, right, neutral. You know, if you wanted, you could make yourself a cheat sheet if that helps you, right? These are neutral, these are basic. And then we'll get to acidic in a second. And so now we look at acetate. And so what, I was just tacking on a hydrogen to try to help, but what acid is acetate from? So acetic acid, and again, right, we can remind ourselves, go back to our chart here, if we need inspiration. Is acetate on here by any chance? Oh, there it is. It's written in a different form, so watch out for that. So acetic acid, acetate, up, that reminds us, right, that it has equilibrium back and forth. And so now we're saying, okay, if it has equilibrium, and we can write it out, then we're saying that in water, right, we can write our KB reaction. That's essentially what we're doing. So plus water gives us back our acetic acid. And then, of course, right, forms our hydroxide. Once again, right, proving ourselves the definition of a base, where it makes hydroxide ions in solution. And so, yes, our acetate is a basic salt. Questions on that analysis? So then let's look at the last example. So again, recognizing our polyatomics, which maybe we haven't seen some of them in a while. So do we remember potassium, where it's from, or acidic, basic, neutral?
I think it would be basic
Oh, where's it from, though?
from our,
What? Potassium what? Not chloride, but what's the base it's associated with? What's the other anion?
KCl.
But what base is potassium associated with?
Potassium hydroxide?
Yeah, so right, potassium hydroxide, right, remember just tack your hydroxide on, usually. And then, oh yeah, that's a strong ionic compound, fully disassociates. All right, so that just proves that potassium is neutral. And then what about our NO2? What was that called again? What acid is it associated with? nitrous acid, good, right? So that's nitrite. And then we could look at our chart again for nitrous acid. So there it is, oh, right under our weak acid. So again, we can tell equilibrium. And so now, let's write our expression. So again, our Ka is our dissociation here. And then our Kb reaction, now showing the conjugate base, reforming our nitrous, and then making hydroxide once again. So now that proves that our nitrite is basic. And so now, all right, so now we just proved, right, all these scenarios. So any questions about that before we move on?
What does it mean to be neutral? Like acid and base?
Sorry?
What does it mean to be neutral?
So remember the neutral, right, we had established that our salt was just basically the counter ion of our strong base, right? So then, okay, that just means that it's not going to reform, right? And then the anion also has to be neutral, right? So it has to be from a strong acid. So that's what we were establishing. So does that make sense? Yeah, so then we saw, right, in this scenario, so the first salt, right, the anion was still neutral, so those all still came from strong bases. But now, right, the fluoride, the acetate, the nitrite, those were all from weak acids. All right, so let's continue with these scenarios. And so now it gives us this hint. So the salt cation is the conjugate acid of a weak base. So we'll revisit this statement. And the anion is the conjugate base of a strong acid. Okay, well, we know what this is going to be, right? That's going to be neutral. So it's telling us the cation is acidic, which we'll unpack that statement. And the anion is neutral. Okay, so we already knew that about the anion. And then it says an acidic solution will be formed, again, right, if our salt cation is the conjugate acid of a weak base. So let's just see that proven, but then you'll notice that there's only one example, because there's really only one main family of bases. So let's look at our ammonium chloride. And so we'll analyze our ammonium. So what base is ammonium associated with? Now this is where it gets a little bit harder, because right now you have to maybe try to remove a proton. Yeah, so ammonia. Okay, so that's good. And so now, what am I trying to write here? So now we can, maybe that's what I want to start with. Let's show our ammonia first. So, right, we know ammonia is our conjugate base. We add water. Okay, we make, right, ammonia and hydroxide. Okay, we knew that. Now let's write, so this is Kb now. And so now let's do Ka. So, right, this is Kb if it's a basic salt, or for, excuse me, a base, right, for ammonia, it's going to have a Kb. And so now we want to figure out our acid reaction. So again, now we're saying we have our ammonium. It's in water. And so now water is going to deprotonate our ammonium, sorry, hard to say those two, reform ammonia, and then in turn, now we make hydronium. And so of course, right now that's a definition of an acid, something that creates hydronium species. And so now we've proved that ammonium is acidic. Does that make sense there? And so then kind of the hint is, well, all your salts, basically your acid salts that you'll see, they have to be some sort of ammonium salt, or like an amine is what I'm saying. So you could do, this is the famous one if you know it, although I think my reference is becoming slightly outdated. Any guesses as to what this compound is? What's this group? Remember what this is called? Huh? Just a little, it's just a little carbon, so one carbon. So yeah, this is a methyl group. And then if you put it onto ammonium, so I'll just tell you. So this is methyl ammonium as the salt, which would be the conjugate acid of methylamine. Oh, sorry. Lost track of my hydrogens there. I didn't draw very good stereochemistry. Let me redraw that. So yeah, that's methylamine, which it was a Breaking Bad reference. I don't know if anybody's watched Breaking Bad there now. It's an old TV show.
It's not even that old.
I know, it seems so old now, though. I'm behind on the times, but yeah, they did a whole like train heist with the methylamine, if you remember that episode. So that's a compound, and it's obviously good for methylating and making meth. So you add right the nitrogen with the meth on there. And yeah, meth, like literally, again, right, methamphetamine and amphetamine like differ by a methyl group, and the only difference is in potency. So the methyl group is what allows it to cross the blood-brain barrier a lot more readily. Anyways, arguably meth could be better because it requires a lower dosage, but anyways, we won't go down that debate today.
That's what they said about fentanyl.
Exactly. I mean, anyways, again, we won't go down. We'll say that for your papers, the great debate of potency versus dosage. All right, and then the last little bit, this is kind of a little bit of half trivia, and honestly, we're going to revisit aluminum in more detail because this is not the full picture. But basically, this is kind of like it always comes up in Gen Chem trivia a lot. But basically, if we have a highly charged metal ion, which, I mean, is usually aluminum 3+ is what they're talking about, maybe like zinc or something, or other metals that are higher charged. But again, kind of thinking back to the concept that if it's going to be if it's going to be acidic, then it's probably a cation. And so that's kind of where this thought comes in. And so all it's saying is, yeah, if you see aluminum, it probably creates an acidic solution. But like I said, this is not the full story of it either, but we'll save that for third quarter when we talk about complexes. And we'll do a little demo, hopefully. All right, so just remember that aluminum makes acidic solutions, at least for our basic trivia. Oh, other things I wanted to point out. So I had said that I wasn't going to test you over the Lewis thing, and then I put a question in about the Lewis definition because it came up in a Gen Chem. I like to look at the ACS exam when I make your exam too, so I like kind of pull questions. And so in the ACS exam, they did have the definition of what a Lewis acid base is, so I threw that in there. And so just review it. Like I mentioned, we're not going to do it extensively, but it's all about this electron donation. So again, acids, right, accept our electron pair, bases donate. But again, hopefully you're kind of seeing that as we go through the mechanism so it feels more intuitive.
Crash Course Organic Chemistry has a really good video on electron attack.
Yeah, that's a good, so yeah, Crash Course Chemistry is also good. Professor Dave, too, if you ever checked out his videos, I think those are good. All right, let me see, making sure, other thoughts. Oh, the last other thing we should say, so again, I probably won't do this to you this quarter, but we might see it next quarter where I ask you to puzzle through this. So we'll probably kind of look at this, but like I said, we'll practice it more later. It's not going to be on your exam because now your exam's written and in stone. So basically, right now we have a conundrum, which is kind of what I was getting at is generally you want to avoid this, right? Unless you're trying to do some complex system. And so let's just say we're looking at ammonium fluoride. Well, kind of the problem with that is we don't know which is stronger, right? So we have ammonium, which if we remember right, we just established, well, that was acidic. Well, fluoride we established was basic, but now, which is stronger? And so then they kind of lead you through this whole argument. But let's slow it down just a little bit. And so basically, it kind of depends also what you ask Google, is what I'll say, right? And so what you'd probably want to check is the KB of ammonia. So again, this is also why it's like good to remember what the heck is what. And so let's see what I mean by that. I'm just double checking that our value's consistent. Okay, so it looks like everybody says that our KB for ammonia is about 1.8 times 10 to the negative fifth. So again, right, think about what reaction is. That's your KB reaction. So again, ammonia plus now our water, right, to give us our base. So now ammonium plus our hydroxide. Okay, so that's that equilibrium. And then, so then I mentioned, right, well, we want to write our Ka at least. So again, establishing what that reaction is. So the Ka reaction, like we had said, is when we take our ammonia, again, react it with water, and then we'll reform our ammonia and then make hydronium. All right, so there's our two expressions. And then we have to understand our next relationship. And so let's kind of look back at our notes. Let's see if it's in our notes. I'll probably just rewrite it. Or maybe we didn't write it. Okay. maybe we didn't write it. But again, so these are all our Ka reactions. And we could even, again, break it down more simply. So we want to have, right, let's just kind of, let's do our generic one for a second. Because again, this will come up later. So not so important now, but we want to see this. So again, right, I'm just kind of rewriting our Ka expression generically, right, what it means. So Ka, hydronium, plus A minus, right, we said Kb, then is then our base, plus water, gives us Hb plus hydroxide. And so now we need to find, right, our relationship between the two. So that's kind of our problem, is that whatever number we look up, right, we want to be able to get the true number that we're looking at, right? So we need our Ka. And so now we have our relationship. And so let's see what happens. So now we'll do a quick derivation. So let's rewrite our expression. So obviously our Ka. So now I'm writing it as our equilibrium expression over Ha. And I want to do Ka times Kb right now. I'm proving this. So now we have, right, Ha, since this is our same acid, right? So Ha times hydroxide, though, over A minus. So write our base expression. And so basically this cancels out and then leaves us with Kw. So then we get what we want to get at, which is Ka times Kb equals Kw. So that was just a long way to say, now we can finally calculate, right, our strength that we need. So now we're saying, okay, well, if we have the Kb, and again, right, you don't know what you're going to be given on exam or like you're Googling on the internet. And so we just want to be able to look at it and understand. And so now we can verify this with our calculator. And so now we can say 1 times 10 to the negative 14 divided by our Kb, because we want our Ka for this one. All right, so now I have my Ka. And so let me write my Ka. So 5.55 times 10 to the negative 10, so that's my Ka. And so now let's see. Let's check our K, either our Ka or our Kb, right, of fluoride. So I believe we have our Ka here, right? So this is our Ka. Well, let's figure out our Kb. Yeah, so that's just the Kw again. Remember the water product constant. And so then our K, now I got confused. Our Kb, sorry. So our Kb, right, a little bit smaller. So now let's write that down. So our Kb is 1.47 times 10 to the negative 11. Okay. And so now all that is to say, and I think they worded it kind of confusing, right? So they say, well, HF is a stronger acid than ammonium. So the Ka of ammonium is larger than the Kb of fluoride. But, I mean, for me, that's hard to see. So I like just calculating the numbers, or else I won't know. So again, right, all you do is you calculate your two strengths. So we found our Ka of our ammonium, right? We found our Kb of fluoride, just based off of the opposite, right? Because again, you'll probably be given a Kb, because this is a base. You'll probably be given a Ka for HF, because that's your acid. Find your strength, and then we see, okay, well, the acid is slightly more, right? It's not much more, but it's the -10 versus -11. So this is greater, so it'll be more acidic. Does that make sense? So like I said, I don't think that's going to be on this exam. I think it will come up next quarter because we're going to practice more with this Ka, Kb type of relationships and stuff. So that's kind of where we're headed, and it gives you a peek. But, so like I said, we'll revisit that later. And then the last little bit of titration, I didn't really go over. So we've kind of been doing the stoichiometry of it, right? That's all to say. It's just a bunch of stoichiometry. Yay! And write solutions. So don't forget molarity. Again, moles over liters. So you won't be tested over anything, over your units explicitly, but there could be a titration problem. Although now I don't remember if I actually did put a titration problem in. And yeah, so we saw this, we did this in lab. We know what an indicator is, right? You just pick your appropriate indicator. So in that case, we picked our phenolphthalein, and we can look at these indicators. And so we're trying to catch it. So if you look at this curve here, right, I think I mentioned this in our pre-lab lecture, but if we're doing our strong acid versus a strong base, right, we're going to get a very strong, or very steep, inflection point here. So, right, we're trying to get it right at that equivalence point. So that's why we pick phenolphthalein and trying to go right for the lightest pink so we catch it as early as possible. Obviously, right, we could have picked something different. Maybe bromothymol blue would have helped us, right? Just try to get it to the green, to that 7. And then just thinking about, what you could do in the future, or like analytical chemistry. Sometimes, right, they work through these polyprotic acids. Actually, I think we'll do a polyprotic titration, or at least attempt to, with our probes, and kind of see that. And ideally, right, with your polyprotic acids, you'll have multiple equivalence points. And so again, depending on those equivalence points, so we'll get into all this third quarter because we have to talk about other relationships. But basically, you could, predict where your equivalence points were and maybe select other indicators like thymol blue, for example. So that's, right, a common one used with those 2 distinct points. Otherwise, right, chemists tend to just use like a pH probe, and so you get a live reading anyways. But all right, I think that summarizes our chapter here. So we'll go ahead so we can take our break / our quiz. So I'll hand out our last quiz on chapter 19. And again, feel free to take a break. Oh, I have homework and also the other cheat sheet. Sorry, I forgot to put it out. So, grab that. You didn't grab it. And then otherwise, I'll see you in lab. Okay. Not enough? Oh, it's supposed to be enough for down the road, but it's just in this town.